Hey everyone, today we're tackling a fun Leetcode problem called push dominoes. It's like setting up a real domino chain, but with a few twists. We'll break down how the dominoes fall and figure out the final state. Ready? Let's dive in. Okay, so here's the setup. We have a line of dominoes, standing upright. Some are initially pushed, left, some right, and some are just standing. Every second, a falling domino pushes its neighbor. A right falling domino pushes the one to its right, and a left falling one pushes the one to its left. Now the tricky part, if a standing domino gets pushed from both sides at the same time, it stays standing because the forces balance out. Also, a falling domino doesn't add extra push to one that's already falling. Our goal is to figure out what the line looks like after all the pushing stops. Let's look at the first example. The first pushes right, but the second domino is already an N, so nothing changes there. The second also pushes right, towards the dot. The pushes left, also towards the dot. Now, according to the rules, if a domino, the dot in this case, gets pushed from both sides simultaneously, it stays standing due to balanced forces, so the dot remains a dot. The final state is exactly the same as the start. Okay, this second example is longer. Let's visualize this. The initial at index 1 immediately makes index 0 fall left. The at index 3 pushes right. The between them gets pushed left and right, so it stays standing. So we have, now, that starts pushing the dots to its right. The at index 7 starts pushing left. They are 3 dots apart. The turns the first dot right, the turns the last dot left. The middle dot gets pushed from both sides, stays standing. So we get next, LR. They push away, nothing happens between them. Then, buckets push from mansions, 2 dots apart. The pushes the first dot right, the pushes the second dot left. They meet perfectly. So it becomes, finally, the last pushes the dot next to it left, and the last dot remains standing. The final result, it follows specific patterns. So how could we solve this systematically? Simulating it second by second seems tricky. Keeping track of which domino pushes which, and resolving the balanced forces at the exact same time step sounds complicated and maybe slow. There might be race conditions if we're not careful. What really matters for a standing domino? It seems to be about the nearest push from the left, which must be enduring, and the nearest push from the right, which must be enduring. This gives us a couple of ideas for better approaches. Okay, first idea. Let's break the line down into segments. Imagine we put a fake at the very beginning, before the first domino, and a fake at the very end, after the last one. Now we look at the pieces between the actual and around, and our fake boundaries. For example, if we have RL, the segments R, fake L, RL and L, fake R. We can figure out each segment independently. Let's look at the types of segments between a left boundary I and a right boundary J. If we have at I and at J, like LL, everything in between will eventually get pushed left. So it becomes all. Similarly, if we have at I and at J, like R tron, everything falls right. If we have at I and at J, like LL, the push is left and the push is right. They push away from the dots in the middle, so the dots stay standing. It remains LR. The most interesting case is at I and at J, like RL. They push towards each other. If the number of dots between them is, say, K, they'll race towards the middle. If K is even, they collide perfectly, and you get half and half. If K is odd, there's a single domino exactly in the middle that gets pushed from both sides simultaneously, so it stays standing. You get some, then X, then some. So the plan is, add a fake at the start and at the end. Find the positions of all the L's and R's, including our fakes. Then, loop through pairs of these positions. For each pair, check the symbols, or if they're the same, or fill everything between with that symbol. If it's do nothing. If it's figure out the halfway point, fill with from the left and from the right, maybe leaving the middle one, as if the distance is odd. Finally, join it all up and remove the fake boundaries. Here's another way to think about it. Forces. Imagine each sends out a push right force, and each sends out a push left force. The strength of the force gets weaker the farther away it travels. For any standing domino, a dot, we want to know, what's the strength of the rightward push reaching it, and what's the strength of the leftward push? How can we calculate these forces? Let's do 2 passes. First pass, left to right, calculating the rightward force. We start with 0 force. If we see an asymptote, the force jumps to maximum, let's say the total number of dominoes. If we see an asymptote, the force drops back to 0, because the blocks any rightward push from before it. If we see a dot, the force decreases by 1 from the previous position, but can't go below 0, We store these forces. Second pass, right to left, calculating the leftward force. Same idea but mirrored. Start with 0. Cn force jumps to 0. Cn force drops to 0. C a dot, force decreases by 1 from the previous right side position. Store these two. Okay, now we have two arrays, one showing the strength of the right push at each spot, and one showing the strength of the left push. We just need to compare them. For each position, if the rightward force is stronger than the leftward force, the domino falls right. If the leftward force is stronger, it falls left. If the forces are exactly equal, or both 0, the domino stays standing. We build our final answer string based on these comparisons. Here's the code for the force calculation approach. First, we create an array. Let's call it initialized to zeros. We do the left to right pass, calculating the rightward force, and adding it to the array at each spot. Then we do the right to left pass, calculating the leftward force and subtracting it from the array. Now the sign of the number in the array tells us the result. Positive means right, negative means left, and 0 means standing. We just convert that array into the final string. Pretty neat, right? So how efficient are these methods? Both the segment analysis, approach 1, and the force calculation, approach 2, are pretty good. For time complexity, both run in big O of n, or order n time, where n is the number of dominoes. This is because we basically make a few passes through the domino line, but the work we do is proportional to the length of the line. We don't have any nested loops that depend on n squared, or anything slow like that. For space complexity, both approaches use some extra memory. The segment approach needs space for the indices and the answer, while the force approach needs space for the force array and the answer. Both use order n space. It's possible to optimize the space slightly, maybe even to constant space if you're very clever, and modify the input in place, but order n space is perfectly acceptable here. Alright, let's recap the main ideas. The core challenge is figuring out how the pushes from left and right interact, especially the balanced force rule, where a domino stays standing if pushed equally from both sides. We saw two main ways to solve this efficiently. First, we could break the problem into segments defined by the and solve each segment based on its boundary types, remembering the special collision logic for the case. Second, we could think in terms of spreading from the and. By calculating the net force at each position after two passes, we could directly determine if a domino falls left, right, or stays put. Both methods get us the right answer efficiently. Hope that explanation of push dominoes made sense. It's a neat problem with a couple of cool solutions. If this helped you out, hitting the like button would be awesome. Feel free to subscribe for more Leetcode breakdowns, and drop any questions or thoughts in the comments below. And hey, if you're feeling extra supportive, the Boba Fund link is always appreciated. Happy coding, and see you next time.